In this video, we're going to look into another important question, which is, what is the need for complex numbers? In the previous video, we did see just a quick definition of what is a complex number. But in this video, we are also going to see why is it required. What is the need for a complex number? Alright, now here starts the answer. Now consider a comma b are natural numbers such that a is greater than b. Alright, consider a and b, which are natural numbers, okay, such that a is greater than b. Now then, in that case, the equation x plus a equal to b is not solvable in the set of natural numbers, right? Now, a and b are of course natural numbers, but is x going to be a natural number? No, because when a is greater than b, let's say assume x plus a is 6 and say b is 4. X will not belong to a natural number because x will be negative 2 here. Negative 2 plus 6 is going to be equal to 4, right? So negative 2 does not belong to a natural number. So therefore, the set of natural numbers is extended to form set I of integers. The set of natural numbers is extended to form set Z of integers just to solve all kinds of equations of the form x plus a equal to b, where a and b are natural numbers. Alright, because integers are nothing but numbers on either side of 0. It also has 1, 2, 3, 4. It also has got 0 and it also has got negative 1, negative 2, negative 3 and so on. So that's how integers came into play when you could not solve this equation just in the set of natural numbers. Alright, so now moving on, once integers was formed by the extension of natural numbers, this equation could be solved. That is x plus a equal to b, where a and b are natural numbers, could definitely be solved. Now there's another condition or another situation where we have x a equal to b, where a comma b belong to integer. At the same time, a is not equal to 0. So now, can this equation be solved in the set of integers? Well, no, it cannot, because now a is not equal to 0. So what happens? Let's take the same numbers, 6 and 4. So we have, say, x6 equal to 4. X will be equal to what? It will be equal to 4 by 6, which is 2 by 3, which is a fraction or a decimal. And it definitely is not an integer, because integer are only numbers which are both positive and negative, and it has to be whole numbers 0, 1, 2, 3, 4 and negative 1, negative 2, negative 3 and so on. It cannot be fractions or decimals. So now to solve this equation xa equal to b, where a is not equal to 0, the set of integers was extended to form, or it is extended to obtain a set of numbers called rational numbers denoted by q. So when the set of integers was extended to obtain a set of rational numbers, which is denoted by q, then all the equations of the form xa equal to b, where a is not equal to 0, could be solved uniquely, where a comma b belongs to integers. Alright, so that's fine. So first we start off with natural numbers. We cannot solve this equation in natural numbers. So natural numbers is extended to the form to form the set I of integers, where this equation can be solved. But again, we have another equation xa equal to b, where when a is not equal to 0, this cannot be solved in the set of integers, and therefore integers is extended to form a set of another number called as rational numbers denoted by q, where this could solve the equation of the form xa equal to b, where a is not equal to 0 and a comma b belongs to integers. Solve every time uniquely. So that's rational numbers. So now then again, we have another set of equations like this: x squared equal to 2, x cubed equal to 3. But these equations are not solvable in rational numbers, because there is no rational number whose square is 2, right? There is no rational number whose square is 2. So now, nor there is any rational number whose cube is 3, right? They are all irrational numbers. Therefore, well, I shouldn't have told you the irrational number part, but anyways. So therefore, the set of rational numbers was extended to form another group or it was extended to form another set of numbers, which is the set R, which is called as the real numbers. So the real numbers is a group of numbers which has got both rational and irrational numbers to it, and that real numbers R could solve these equations, x square equal to 2 or x cube equal to 3, and those kind of equations. But again, now, is this gonna not be able to solve another set of equations, and is it gonna lead somewhere? Well, yes. Let's see what it is. So now we've got another set of equation, x squared plus 1 equal to 0 or x squared plus 4 equal to 0, which are equations which cannot be solved even in real numbers. Say for example, x squared, let's solve this equation, x squared equals 0 minus 1, which is negative 1, and we have x equals square root of minus 1. Well, we do not have real numbers. We cannot solve, or we do not have real numbers such that x equals square root of minus 1. So now comes the concept of complex numbers. This is where the complex numbers comes into play. Well, Euler, the mathematician, so Euler was the first mathematician to introduce the symbol I, which is called as the iota, for the square root of minus 1. That is a solution of x squared plus 1 equal to 0 with the property, let me write it in brackets here, I squared equals minus 1. So therefore, if I squared equal to minus 1, I will be equal to square root of minus 1. Right? So he also called this symbol as an imaginary unit. So that is how we have complex numbers. Okay, that is also we have how do we, or why do we have the complex numbers? That's one question also being answered here. But apart from it, we also know what is the need for complex numbers. Well, here is the need, because you cannot solve, we do not have the numbers in real numbers to solve these kind of equations, x squared plus 1 equal to 0, and therefore comes the complex numbers and the concept of I, which is called as iota, and it is also an imaginary unit, and the mathematician who introduced that was Euler. Alright, so that ends this video, or basically that ends the question, what is the need for complex numbers? We've got an answer here, so that ends this video. I'll see you in the forthcoming videos with more concepts based on complex numbers.